Chemical reactions occur at different rates, but it is possible to influence the rate of reaction by numerous factors. The collision theory states that the rate of reaction is dependent on the frequency of collisions. However, these collisions are only effective if they have enough activation energy to break bonds to begin the reaction, and if they collide at the right orientation to form new bonds. Factors that will be explored that increase the rate of reaction either increase the frequency of collisions or make the collisions more effective. The rate of reaction can be measured by the rate at which reactants are used up or the rate at which products are formed. This is known as a reaction's lifetime. The rate of reaction is measured by the reaction's lifetimes, but not all reactions have suitable lifetimes that can be observed. The reduction of purple permanganate ions by sulfide ions was observed by firstly, rapidly mixing the reactants together, and secondly, forming two separate layers of the reactants and then mixing them together. The reduction of purple potassium permanganate by oxalate ions was also observed. There were two stages in the reaction. Firstly, potassium permanganate reacts with sulfuric acid, and one of its products is manganese heptoxide. Secondly, the manganese heptoxide will oxidize the oxalic acid to carbon dioxide. This intermediate step is not included in the reaction formula. Gases tend to react faster than liquids, which react faster than solids, as it takes energy to separate particles from each other. Because of this, the state of the reactant is a factor affecting reaction rate. This is demonstrated by comparing crystal and aqueous solutions of the reaction of lead ions and iodide ions to form yellow lead iodide. The aqueous solution reacted instantaneously, much faster than the crystals. The surface area of a solid substance is related to the solid's reaction rate. The effect of surface area on reaction lifetimes was shown by the reaction of hydrochloric acid with powdered marble and marble chips in the setup as shown. The blue balloon containing the powdered marble chips was noticeably bigger than the red balloon containing the marble chips. This is because the powdered marble reacted faster than the marble chips. This is because by increasing the surface area, more particles are available to react, so the number of collisions increases and thus the reaction rate. The dependence on the rate of reaction on the concentration of reactants was investigated by the reaction of magnesium and hydrochloric acid solution of different concentrations. The reaction of potassium iodate solution and starch and hydrogen sulfite solution was observed by changing the concentration of potassium iodide with distilled water. Both reactions slowed when the concentration was decreased. The collision theory states that the rate of a reaction is dependent on the frequency of collisions. Increasing the concentration of the reactants increases the amount of collisions per second and therefore increases the reaction rate. Temperature is proportional to the amount of kinetic energy of a substance, and so with an increase in temperature, particles are provided with enough activation energy to ensure more successful collisions. The frequency of collisions is also increased. The test tube containing a catalyst had a faster and more vigorous reaction. A catalyst alters the rate of reaction by bonding to a reactant molecule, and thus weakening a bond which must break for the reaction to take place. A catalyst is not being consumed in the reaction. The oxidation of tartrate ions by hydrogen peroxide in aqueous solution, catalyzed by pink cobalt ions, demonstrated that a catalyst can participate in a reaction without being consumed in the reaction. The green color is a complex form of cobalt which formed as the catalyst was involved in the reaction. The pink showed that the cobalt ions were present but not involved. Light is a form of energy. Light speeds up a reaction by providing more energy to particles, resulting in an increased frequency of collisions and allowing particles to reach the activation energy required. As this reaction is light sensitive, it is often used in modern cameras to create a photographic image.